So this video is dedicated to some of the final stuff you're going to do in 4.3 and then also 4.5. It's kind of taken from 4.5, but I also think that it's very helpful when you're applying it to 4.3. So hopefully you can watch this video before you do 4.4. I'll indicate the parts where you might want to watch 4.4 just to understand. There are only a couple things. It actually only has to do with one of these list of things. The rest you can skip to this video right after watching the videos for 4.3. And if you want more examples about how to handle things that you see at the end of 4.3, this is the video you want to watch, at least the first couple examples. Okay, so the whole idea is sketching curves. And 4.5 kind of gives you a bunch of guidelines to follow. And as you're doing the homework for 4.5, it's going to remind you of those guidelines. It's going to say, here are the guidelines, make sure to follow them now, apply it to these functions. And so what we're going to do today is we're going to look at a couple different functions. This is the first one, and we're going to learn what the guidelines mean as far as the functions are concerned. And then at the end, we're going to try to graph them. So what are the guidelines? Given a function, if you want to sketch its graph and you want to get a good idea for it, then what you want to do is you want to answer or describe all of these different things as much as you can. And you want to use calculus if you can. So the first one is going to be domain. You want to talk about what the domain of the function is. That's pretty easy. You don't need calculus for that. Next one, intercepts. If you can find the intercepts, that's great. X-intercepts, Y-intercepts. Y-intercepts are usually a lot easier to find than the X-intercepts. We'll talk about that. Again, you generally don't need calculus for that. Symmetry. Is it an even or odd function? If you know it's symmetric in some way, that can help you sketch it. The examples I chose, I don't think have any symmetry to them, but as you kind of go through different things, if you remember what it means to be an even function, if you remember what it means to be an odd function, it's like when we're graphing sines and cosines. We really only need to know what's happening on one side of the y-axis, because the other side has symmetry to it, whether it's even or odd. Asymptotes and end behavior. This is where you start getting into calculus. In order to know asymptotes, we have to be taking limits. And in order to know end behavior, that's limits of the function at infinity, you have to know some calculus. So this is the point where you might need 4.4. Because when we're taking limits at infinity, we might need to use L'Hopital's rule. So remember, this is L'Hopital's rule. The other one is intervals of increase or decrease. So this was from 4.3. Local maximums and minimums. Again, that's how we determined when we had a local maximum and a local minimum, was using the first derivative test or the second derivative test. So again, 4.3. Concavity / inflection points, that's again 4.3. So these are where we use calculus. And in particular, this is 4.3. In particular, one thing you want to keep in mind is that we're going to need not only f, so this is, if you want to think of it as guidelines for sketching the graph of a function, these 3 points, E, F, G, they're going to be so important. We're going to need F prime and F double prime to answer those. Okay, so in a second we'll get started with this example here. All right, so when you're given a function and you want to graph it, at this stage, because we know a little bit of calculus, we know things like increasing, decreasing tests, concavity tests, things like that. Assuming you've watched the videos for 4.3 so far, the first one and the second one. What we're going to need when we graph this is we're going to need information about f prime and then also about f double prime. So we're going to need to compute the derivative of the function and its second derivative. Once we have that, we'll be able to answer all of our questions. So we'll just have to analyze the data, answer them. Okay, so this is generally the hardest part, is getting the second derivative, because it can get a little messy, but you want to, apply all of the knowledge that you have, get that second derivative, and get it going. So first derivative, pretty simple. We have a product of two functions, so let's use the product rule. Okay, so I have to take the derivative of x to the 3/4, that's going to be 3/4 x raised to the negative 1/4, and then it's going to be times x minus 2 squared. So derivative of the first function times the second function plus the second function, or the first function, x to the 3/4, times the derivative of the second function. So times 2x minus 2 raised to the 1, because I'm using the power rule there. All right, before we move any further, I'm going to simplify this. And the reason I'm going to simplify it is because I'm going to need to solve for zeros of this equation. I'm going to need to take the next derivative, and it's a little bit easier to take when it's simplified. So let's go ahead and do that. So what you want to do is I always like to pull out the lowest power of any term that shows up that has a variable in it. So for example, I have x to the negative 4th and x to the 3/4. So I'm going to pull out an x to the negative 4th. I'm also going to pull out an x minus 2 raised to the 1. And then what am I going to have left over? I'm going to have, well, I pulled out this x. I pulled out this x minus 2, but I only pulled out one of them, so I have an x minus 2 raised to the 1. And when I pulled out negative 1/4, that adds 1/4 to this x, so that becomes x. I pulled out this x minus 2, and what I'm left with is a 2 there. And then if I kind of left that 3/4 in there, that would be fine. But what I'm actually going to do is I'm going to pull out the fraction and leave the 3 in there. But when I pull out a 4th from all this, I have to counter that by multiplying this term that didn't have a 4th by 4. Okay, so what does this all become? This all becomes 1/4 x to the negative 1/4 times x minus 2. And then this term here becomes 3x minus 6 plus 8x. And if I combine all of those, what I get is 11x minus 6 times x minus 2. And then 1/4 x to the negative 1/4. And this is my first derivative. Okay, so what's neat about this is when I set this equal to 0, I'm going to know exactly, it's already kind of factored. So it's already nicely factored. I can make these parentheses instead of brackets because I'm kind of done. All right, so that's all well and good, and that's perfectly fine. What I'm going to do now is I'm actually going to multiply this out because I'm going to get 11 x squared minus 6x minus 22x, so minus 28x plus 12. Okay, so that's all well and good. And the reason I did that is because now when I take the second derivative, I'm going to get two functions, and I have to use the product rule again. And so the first is going to be derivative of this, so I'm going to have negative 4 times 1 over 4 x to the negative 5/4 times this function, 11x squared minus 28x plus 12, and then plus this function, 1 over 4 x to the negative 1/4 times the derivative of this, which is going to be 22x minus 28. All right, now what we're going to do here is, again, I'm going to simplify things. What I'm going to pull out is I'm going to pull out an x to the negative 5/4, the lowest value that shows up. And then I'm also going to pull out my fractions. So since I have a 1/4 here, and I have a negative 1 over 16 here, because 1/4 times 1/4 is 1 over 16, I'm going to pull out a 1 over 16. And then what I'm left with is I took all this term from this first one, so I just have a negative, because I have a negative, 11x squared minus 28x plus 12. And then I have plus, because I took out negative 5/4, I have to add 5/4 to that. That's going to counter that and give me just an x. And so I have x by itself. But since I took out 16 instead of 1/4, it's going to be 4x. And this is going to be 22x minus 28. And we'll simplify that all in a second. So again, this is going to be x to the negative 5/4 divided by 16. All of that times, if I multiply this out, I get 88x minus, this becomes 32, 112. And 112x, because I have an x there. And so now if I combine these, I get 88x squared minus 11x, 77x squared, 11x squared. And then I have negative 112x plus 28x. That's going to leave me with minus 84x. And then I'm going to have this minus 12 here. Okay, so that's going to be how we take the second derivative. And then we'll be back with what to do with this information. Okay, so here I've just kind of rewritten all of our information. We have our function here. We have its first derivative. We have its second derivative. And now we're ready to answer all of these questions. Okay, so what's the domain of our function? Well, the one thing you want to watch out for is, do I have a radical? Do I have something like natural log? Do I have something like zeros in the denominator that can show up? Those are the things you want to watch for. So what types of functions am I using? And I don't have any natural log functions or logarithmic functions. I don't have anything that could go 0 in the denominator because I don't have any negative exponents. That's fine on my first function. But I do have this thing that's, it's the fourth root of x raised to the 3 times x minus 2 squared. So this is a fourth root because I have a 1/4 in there, or a 3/4 in there. So what does that mean? It means we can only plug in non-negative numbers. So the domain is going to be from 0 to infinity. And we're done there. So B, what about intercepts? Well, there's y-intercepts and there's x-intercepts. And the y-intercepts are actually really pretty easy. The y-intercepts are when you plug 0 into your function, what do you get? It's going to be that point. Well, I plug in 0, I get 0 out. So that means the y-intercept is the point 0, 0. Okay. What about the x-intercept? Well, x-intercepts, that's when your function is equal to 0. Well, when your function is equal to 0, that's this expression. X raised to the 3/4 times x minus 2 squared. Since it's a product of two things, one of them has to be 0. Well, that tells you that x can be 0. X could also be 2, and that'll make your function 0. So that tells you that the x-intercepts are the points 0, 0, which we actually already knew about, and the point x equals 2, y equals 0. So those are going to be the points where it touches the x-axis. Okay, C. There's no symmetry. And this is kind of an unimportant one because you can still graph it without knowing the symmetry. The symmetry is just going to be helpful if you recognize that it's either even or odd. And if you want to know how to tell if something is even or odd, come talk to me. You can find it, I think we talked about it at one point, but there's not going to be any symmetry to this one, so just trust me on that. Okay, D, asymptotes and end behavior. Well, our function doesn't have any asymptotes. Remember, asymptotes are points where if you take a right or left limit, it's going to go off to infinity. We don't have anything, or negative infinity. We don't have anything like that. You can look at all the values in the domain. Notice that we have this open interval, this closed interval here. If we had things like open intervals in our domain, if we knew that it approached a number but it never actually took on that value, so like if there was something in the denominator that we couldn't plug in, something like that, that might clue you in that there's an asymptote. We don't have anything like that. But we can talk about, so no asymptote, but we can talk about end behavior. And what that means is, what about the ends of your domain, the ends of your intervals on your domain? Since we have the limit, or since our domain goes off to infinity, we can consider the limit as x goes to infinity of f of x. And this is just going to be equal to the limit as x goes to infinity of x to the third over 4 times x minus 2 squared. And this is just going to be infinity times infinity. Infinity times infinity is not one of our indeterminate forms because it's just going to be infinity. So you're good there. So we know it's going to shoot off to infinity. Okay, so we're done with those things. Now we have to talk about intervals of increase and decrease. And how do we do that? Well, what we're going to do is we're going to figure out where our first derivative is positive and where it's negative. That's going to tell us the increase and decrease. And so what we have is we know our function starts at 0. And we want to find where our first derivative is equal to 0. So if we find where our first derivative is equal to 0, that means that this expression, x to the negative 1 over 4 times x minus 2, 11x minus 6, has to be equal to 0. Well, this is where how we wrote it like this is very fortunate, because we can never plug into 0 into our function because we have a negative exponent here. That would be undefined. So this really isn't adding anything to your factor. But when is this 0? It's going to be 0 when one of these things is equal to 0. This can never be 0. This thing here can be 0 when x is equal to 2. This thing can be 0 when x is equal to, well, 6 over 11. All right, so we have these two other points, and they're both to the right of 0. The furthest one is 2, because we know 6/11 is smaller than 2. And then, actually, it's closer to here, is 6 over 11. Okay, so what we have to do is we're not worried about anything to the left of 0, because our domain only starts at 0. So we have to pick 3 points. One in between 0 and 6/11, the other one in between 6/11 and 2, and another one after that. And so I'm going to choose the points 1/2. That seems convenient. 1, that's between 6/11 and 2, so you can think 1/2 is somewhere here. This is going to be 1, and then 3, why not? And then 3. And all I have to do is plug it into my function here. And one thing you want to worry about is we're not worried about the actual value right now. All we're worried about is whether or not our function our derivative is positive or negative. So what do? We plug 1/2 into here. We know that's going to be a positive number, whatever it is. Plug it into here, you're going to get a negative number. 1/2 minus 2 is negative. Plug it into here. Maybe you'll have to do some calculation, but you can see, if you think about it, that's going to give you another negative number. So you'll get a positive times a negative times a negative. And that's going to be greater than 0. So we know from 0 to 6 over 11, the derivative is positive. So our function has to be increasing. All right, what happens when we plug in 1? This is going to be positive, this will be negative, this will be positive. So you'll get positive, negative, positive, which is smaller than 0. So on this interval, it's going to be negative. And then 3, well, you could probably see you're going to get a positive times a positive times a positive. Positive, positive, positive when you plug in x equals 3 to these things. And that's going to be greater than 0. And so this will be positive there. And so just to kind of bring it home, your function is increasing on 2 intervals, 0 to 6/11 and 2 all the way off to infinity. And it's decreasing on the interval 6 over 11 to 2. All right, so now let's talk about f, local max and local min. Well, f will have a local max at what value? when x is equal to 6/11. How do I know that? Well, I know my function is increasing and then it starts decreasing after that. And I know the derivative is equal to 0, so that's going to indicate a flat tangent line. So if it's increasing, flattens out, and then starts decreasing, this has to be a local maximum. And it will have a local min at x equals 2. Again, if it's decreasing and then it starts increasing, well, that has to be a minimum value. And then after that, we know it's going to shoot off to infinity. So we know that this is indeed a very much local maximum because we can take values that shoot off to infinity, any high value you want for your function. But what's going to be interesting about this is notice that if we compare it to what you get when you plug in 0, you're going to get 0. We also can see if you plug in 2, you're going to get 0. So this is actually the lowest value you can take. When x is equal to 2, you're going to get 0. It's never going to go smaller than that. And you can reason that because it starts at 0, it increases, then it starts decreasing, and it hits a minimum value on that decrease at 2, which is going to be equal to when your function is 0, and then it starts increasing again. It never decreases after that. Okay. All right. So now we're going to talk about concavity / inflection points. So this is going to get, actually, let's see. Let me see if I can, I know what the domain is. I have all this written down, so I'm going to make some room here. Okay. So this is G, concavity / inflection points. All right, so now what you want to do is you want to look at your function f double prime of x, and you want to set this equal to 0. So this is where you have to think, when is this expression equal to 0? Well, it turns out that this is going to be equal to 0, again, when this or this is equal to 0. Since this will never be equal to 0, because I can't choose any x values except positive x values, because I have a negative in the exponent, this means that this gross quadratic has to be equal to 0. All right, so I'm going to throw in some magic and say if I use the quadratic formula, then what I'm going to get is I'm going to get two values. X is about equal to 1.219 and about equal to negative 0.128. Those are the two values that this is going to be equal to 0. About those values. One of them I can throw out. I can throw this one out, and what's the reason for that? This is a negative number. It's outside of the domain of f. It's not going to show up as an inflection point. It's not going to show up in your domain at all. We're not worried about that one. So we just kind of need to focus on this thing here. And so if I'm looking at f prime on the interval 0 to whatever this x value is here, call it 1.219, and then everything after that, what I want to know is is my second derivative positive or is it negative from 0 to this value and from this value on? Well, I can choose test points. I can do that too. Or I can notice that this term here, this quadratic, it's going to be shaped like this. So if I just graph this piece of the derivative of the second derivative of f, it's going to look like this. So in between its x-intercepts, it's going to be below the x-axis. So this piece is going to be negative from this, negative value here to this piece here. It's going to be under the x-axis. And then after that, it's going to shoot above it. So I know that my second derivative is going to be negative during these values. And you can pick a nice test point. You can plug in 1. That's fine. You're going to get something negative there. Or you can reason like that and then know after that it's going to be positive. Actually, it's pretty easy to see that 1 is going to be negative. You're going to get 77 minus 84 minus 12 and then 1 up here. Going to give you a negative number. So you're going to get negative and then positive. What does that mean about your function? It means that from 0 to this point here, it's going to be concave down or below all its tangent lines, and then concave up or above its tangent lines. All right, so let's put all of this information together to graph it. Okay, so what I've done here is I've drawn a Cartesian coordinate system. I have the origin here, and I know my graph starts at x equals 0, and that's also going to be where y equals 0. So it goes through the origin, and it's also going to hit the x-axis at 2. What else do I know about it? Well, I know that it's going to have two local extrema, one maximum, one minimum. 2 is going to be a minimum. It's going to hit a maximum at this x value, whatever that is. And for that, it's going to be increasing, and then it's going to start decreasing until it hits 2. What do we know about this point, 1.219 for x? We know there's going to be an inflection point there. So we know that our graph is going to be below its tangent lines until about this point. And then it's going to kind of switch to being above its tangent lines. So you can kind of see how that switch is made there at this point here. That's the point of inflection. And it stays like that, and it shoots off to infinity. And so you can see that's, what all of that information kind of brought us. And things that aren't important. Well, I know that this is going to be whatever the function is at 6/11. I don't need to know exactly what that is. I can still get an idea. Why do I know it looks like this? Because I know it's increasing on that interval. I also know that it's below its tangent line. So if I draw a tangent line, I want it to look like it's below those tangent lines. And then after this point, I want it to look like it's above those tangent lines. So that's kind of important things. I know it starts here and it hits the x-axis here. And so it kind of has to keep like that. I know that it keeps going off to infinity. These are important things. All right, and I know these are a lot of work, but if you work with them, you get a good sense with what's going on. And you can even plug this function into a graphing calculator and get confirmation on this too. It's going to look like this. Maybe I get, it a little wonkier than a computer would, but we get the idea. We get where it increases, we get where it kind of tops out and where it bottoms out, and then where it keeps going. So we have all of the important things in order to sketch it. And you might be thinking, well, I could always plug these into a graphing calculator and things like that. Yeah, you're going to learn to program things that do this for you. But you also want to be able to recognize and spot when those programs might be wrong or when maybe you programmed them wrong. And knowing kind of the basics about these graphs is very important. Knowing where maximums and minimums are, knowing where inflection points are, and what they mean as far as your function. Okay, the next example we're working with is, I guess we'll call this example 2 for this video. Next example is f of x equals e to the x over x plus 3. All right, so our first derivative of this function, you have to use the quotient rule. Derivative of the top times the bottom minus the top times the derivative of the bottom, all over the bottom squared. And I can factor out an e to the x, and I'll get x plus 3 minus 1, x plus 2 over x plus 3 squared. There, this one wasn't so bad. And now we take the second derivative. What are we going to get? Well, have to be a little bit careful here because now our top function is the product of two functions. But we apply the quotient rule again. So we're going to get derivative of the top. That's going to be derivative of the first function times the second function plus the first function times the derivative of the second function. So if we do the derivative of the top, we should get that times the derivative of, or times the bottom, not the derivative of the bottom, minus top function, e to the x, x plus 2, times the derivative of the bottom, which is going to be 2, x plus 3, all of that, over this thing raised to the fourth. Sorry, squared. In the end, it's going to be raised to the fourth. Okay, so what do we do here? These, I'm going to factor out an e to the x. And then from both of these, I'm actually going to factor out an e to the x. I'm going to take out an x plus 3. And what I'm going to be left with in the numerator is going to look like this. I'm going to have a x plus 2 plus 1 times x plus 3 minus, hold out that x plus 3, that e to the x, so minus 2x minus 4. All right, all over x plus 3 raised to the fourth. Okay, now I can cancel out one of these x plus 3's. And I just need to simplify this. And what I'm going to get in the end is e to the x times x squared plus 4x plus 5. All of that over x plus 3 raised to the 3. All right, so you should see that. Hopefully you can see that, yeah. Okay, I've collected that information here, and now we want to start following the guidelines. Okay, so what is the domain of our function? Well, we can plug anything we want into e to the x, that's perfectly fine. We can't plug negative 3 into the denominator though. So the domain is going to go from negative infinity to negative 3, and then also include negative 3 all the way off to infinity. So this is just a fancy way of writing all values except for negative 3. And that u there in the center means union. It means this together with that. That's all it means. It's set notation. This is a set of real numbers. This is a set of real numbers, and we want to join them both. Okay, so now that answers that. What about intercepts? Well, we want to ask ourselves, what's the y-intercept? The y-intercept is going to be when you plug in 0, what are you going to get? You're going to get 1/3. So the y-intercept is going to look like this. 0, x equals 0, y equals 1/3. What about x-intercepts? Well, if I set e to the x over x plus 3 equal to 0, that's going to happen when e to the x is equal to 0. When is the exponential function equal to 0? Never. So, does not exist. Again, remember, throw anything into the exponential function, you're always going to get a positive number. So it can never be 0. You can look at the graph too to answer that. All right, C, symmetry. No symmetry in this case, so don't worry about this. Again, symmetry is just to kind of help you. It's not important. You can still graph it if you know all the other things. Nope. Nope. D, asymptotes and end behavior. Well, it turns out we're going to have an asymptote here because you can see that if I take the limit as x approaches 3 from the right, you can get that this is going to be positive infinity. And if I'm approaching, sorry, not 3, negative 3 from the right of negative 3, you're going to get that this is positive infinity. Well, why is that? This thing is getting closer and closer to 0, so you know it's going to go towards one of the infinities. E to the x is always positive. This thing in the denominator will also always be positive because this indicates you're taking larger than negative 3 values. All right? So, so what we're doing here is we're approaching it from the right. And then, again, if you approach it in the other direction, negative 3 from the left, it's going to shoot in the other direction. So you're going to go out to negative infinity. So when we draw that, you're going to see an asymptote at x equals negative 3. And it's going to kind of shoot in different directions on either side. Okay, what about end behavior? Well, what happens when I take the limit as x approaches infinity of e to the x over x plus 3? Well, in order to do this, I actually have to invoke L'Hopital's rule. Why? Because if I try to take them kind of individually, I'm going to get infinity over infinity. And so I get to use L'Hopital's rule. L'Hopital's rule says, well, this limit will be equal to the limit of the derivatives of the ratio. So, of the ratios of the derivatives. So, you take the derivative of the top, you compare it to the derivative of the bottom, and then you take that limit. Well, this is going to be e to the x over 1. Take the limit as it goes to infinity, you're going to get infinity there. We actually have two end behaviors because we go off to infinity, and remember our domain goes off to negative infinity. So I also have to look at x going to negative infinity of e to the x over x plus 3. Well, this one you're actually not going to have a problem with. Because remember, if I take the limit as e to the x goes to negative infinity, I'm going to get 0. So what am I getting? I'm getting 0 over infinity. This is not an indeterminate form. This means your limit is going to go to 0. So what that implies is that you have a horizontal asymptote at 0. Okay, so what else? Intervals of increase, decrease. Well, now we have to start using our derivative. So what we want to do is we want to look at the first derivative, and we want to say, when is that equal to 0? Well, that's going to be equal to 0 when e to the x times x plus 2 all divided by x plus 3 squared is equal to 0. When is this equal to 0? Well, it's going to be equal to 0 when the numerator is equal to 0. When is that equal to 0? One of these values has to be equal to 0, so it's only going to happen when x plus 2 is equal to 0. That's because e to the x is never equal to 0, so it's only going to happen when x is equal to negative 2. All right, so let's look at these values. And what we want to do is we actually want to include negative 3 in our interval. That's because it's possible that at a value where it's undefined, it changes from increase to decrease. So it can possibly happen like that. So we just want to check at some of these undefined values. All right, so what we want to do is we want to take our second derivative, f prime, and we want to choose test values x. We're going to have to choose 3 test values, negative 4, 1 in between negative 3 and negative 2, so maybe choose negative 3/2, and then some value after negative 2. Let's pick an easy one, 0. In fact, we actually already plugged that in. All right. Now, look at your derivative, plug these values in. What are you going to get? Well, let's just do a double check. The bottom is going to be positive. This one's going to be negative. And this is always going to be positive. So, you're going to get less than 0. So, this is going to be, smaller than 0. That's how you want to indicate it. Okay, so what that means is that on this, it's going to be decreasing. Okay, what about negative 3 to negative 2? Well, plug in this, you're going to have positive value, negative value. This is always positive. This is also less than 0. So this is going to be decreasing on that interval too. And then what about 0? Plug it in. We already know that we get 1/3 when you plug in 0, so this is going to be greater than 0. So that's going to be positive. Great. Okay, so we know it's going to decrease on the intervals negative infinity to negative 3, and also negative 3 to negative 2. Notice I'm not including negative 3. That's because our function isn't even defined there. So it can't be decreasing at negative 3. It can't be decreasing on an interval that it's not defined. And it's increasing from negative 2. I can actually include that. Increasing from negative 2 all the way to infinity. Boom. All right, so what about local mins and local maxes? Well, we really only have one candidate, and that would be negative 2. What is it going to be? Our function is decreasing, 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 and then it starts increasing. So we're talking about f, our local max, sorry, not local max, local min at x equals negative 2. And we can even plug that into our function. It's not going to be too funky. So that's f of negative 2. You're going to get e to the negative 2 over 1, or e to the negative 2, whatever that value is. All right, so inflection points, f. Inflection points, we just answered f. So G, inflection points in concavity. That's going to be when your second derivative is equal to 0, or when this expression is equal to 0. Okay, so what we're going to do is, when is it equal to 0? Well, again, denominator doesn't do anything. It's going to be equal to 0 when e to the x or x squared plus 4x plus 5 is equal to 0. E to the x is never equal to 0. So x squared plus 4x plus 5 has to be equal to 0. All right, when is this equal to 0? Well, this is going to be equal to 0 when x equals negative b plus or minus the square root, using the quadratic formula, of b squared, 16, minus 4ac all over 2 times a. But wait up, hold up. You're going to get a negative number inside the radical. That means your x values are complex numbers. We're dealing with real numbers here. Complex numbers need not apply. So what does that mean? That means that this is never equal to 0 for any real values. We don't have any possible inflection points. Okay, that doesn't mean concavity can't change. Watch this. What we do here is we're going to look at any values where our function might be undefined. We know our function is undefined at negative 3. I'm running out of marker. There we go. Great. That one looks wonderful. Okay. So remember, our function is undefined at negative 3. So what we want to check is we want to check the interval from infinity to, or negative infinity to negative 3, and then negative 3 on. And we want to check the concavity because maybe it switches. Okay, so what do? We look at our function f double prime, pick test points on either side. So I'm going to choose a real easy one, 0 for this side, 0. That's gonna, you plug it into f double prime, you're gonna get 1 times 5 times 3 squared. That's gonna be positive. Boom. So we know on this side of negative 3, your second derivative is positive. All right, what about another number? Negative 4. Okay, so I'm choosing negative 4 somewhere over here. Negative 4, plug it into your second derivative, positive number. This is always positive. What is this? This is going to be negative raised to the third. You're going to get negative 1 raised to the third. That's going to give you a negative number there. So we know the concavity is negative here. All right, we're finally ready to pull it all together. So I've given myself a Cartesian coordinate system, and I'm ready to graph. I know there was an asymptote at negative 3, and I know on the left of negative 3, it shoots down to negative infinity. So we're going to get that the function is going to look like this. That also tells you that it's decreasing on that. As x keeps kind of moving to the right, we know that the function is getting smaller and smaller. We also know that the end behavior was that it gets closer and closer to 0. That means it's getting closer and closer to the x-axis. So it looks like that. All right, so that's what happens to the left of negative 3. We're going to come in like that. Now, to the right of negative 3, remember, from negative 3 to 2, it's going to be decreasing. So that means it's coming in hot from this asymptote, and it decreases, and this is a local minimum value. And then what happens after that is, well, it's going to shoot off, and we know it crosses the x-axis, or sorry, y-axis at 1/3, and then it shoots off to infinity. And we know inflection point wise, this fits with our image here, where at, sorry, not inflection point, but concavity wise, before -3, it's going to be concave down, so all of the slopes are going to be above your function, and then when it flips that, then the graph is going to be above all of the slope lines. So you can kind of see that there. So this is what y equals e to the x over x plus 3 looks like. And for my next videos, I promise I will get new pens. Although I think you guys can see that. Okay, I just read an email where my cats got complimented. So I just want to show you that in my little video studio, this is where my cat sleeps. So at least that's one of them. That's Nobody. She's pretty much always there. So it's kind of fun. Okay, so I know that these videos this week, there was a lot of stuff. So I thank you for bearing with me. I wanted to get through and really give you full in-depth idea of these things. So this will be the last example that I'm going to go through, but it does have 2 parts to it. So I guess it's technically 2 examples. Let me find pens that work. I need to figure out a way to get more pens in quarantine. That'll be fun. Example 3. And this is what's called slant asymptotes. And I probably won't ask you anything about slant asymptotes on midterms and tests, but it is important. I might ask you the ideas about them, like what they are, but they can be a little tricky to find. So here's the idea. So say I have a function f of x equals 1/3 x cubed plus x squared minus x plus 4 over x squared minus 1. Well, a slant asymptote is going to be a line where, so say I have a line here, where if I look at f of x and I subtract that line and I take the limit as x goes to infinity or negative infinity, I get 0. And so what we're going to find is we're going to find in this case that we're going to get a slant asymptote at the line y equals 1/3 x plus 1. So if we were to graph it, it would look something like this. And if you were to look at the graph of the function y equals f of x, this function, what it's going to look like is it's actually going to have these 2 asymptotes. You might be able to guess where they are. The graph is going to kind of look like this between them. And it's going to go like this, and then also like this. And notice how when you shoot off to infinity, these the graph itself, the path it takes, gets closer and closer to this line here. That's the idea behind a slant asymptote. It asymptotically gets closer to that. And all that means, again, is that this is just some line where when we take the limit as f of x minus that line, as they go off to infinity, you get 0. That means that they're getting closer and closer together. Okay, so what I told you was, I told you that this line here was going to be what our slant asymptote is going to be. Well, so let's check that out. So let's just try and see what we get. Well, if we have 1/3 x cubed plus x squared minus x plus 4 over x squared minus 1, and you subtract the line 1/3 x plus 1 from this, well, if I wanted to combine them, I have to give this a common denominator. So what I'm going to do is 1/3 x cubed plus x squared minus x plus 4 all over x squared minus 1 minus x squared minus 1, and then this is going to be times x squared minus 1. Well, when I multiply all that out, what I'll get is 1/3 x cubed, and then, so again, what I'm doing is I'm multiplying this by x squared minus 1 over x squared minus 1. Multiply that out, you're going to get 1/3 x squared plus x squared. Then you'll get minus 1/3 x, and then minus 1. Okay, when I combine these, that's going to cancel with that. This is going to cancel with that. And I'm going to be left with negative 1, should be adding that, negative 2/3 x plus 5 over x squared minus 1. Okay, so now if I take this limit as x goes to infinity, taking the limit of this minus the line, take the limit here, and take the limit here. Well, what do I notice? I notice that I have a linear value here, quadratic here, so this has to be equal to 0. And so that confirms that. So we've confirmed that we have a slant asymptote there. So what this tells you is how to confirm when you have a slant asymptote. You check this limit. So that should at least give you a way to get started, especially if you have kind of a guess on what the slant asymptote is, or someone gives you information, you can check it to make sure. Okay, we're going to do an example where we check for a slant asymptote, where we find a slant asymptote in a second. Okay, so I had to switch to red pen for now. I'll get some black pens that work again. So here's our new function. It's f of x equals the natural log of x minus x squared over x plus 1. Now, the one thing I'm going to ask you to check, and you can stop the video and make this calculation, is check that the limit as x approaches infinity of f of x is equal to negative infinity. Also, if we're thinking about end behavior of this function, this is really the only thing that matters, because we're not thinking about going off to negative infinity, because again, it's a question of domain. You have a natural log function there. You can't plug non-negative numbers in. You can't plug non-positive numbers, actually. You can't plug 0 in. So we're only worried about the right of the y-axis. Okay, so here's the first step. Keep in mind that if I wanted to think of this as maybe this piece over x plus 1 minus this piece over x plus 1, this, as x goes to infinity, is going to go to 0. So this piece is going to go to 0, and all that's really contributing here is that this piece is going to then drag everything to negative infinity. And you can verify that that's actually true. This is going to go to negative infinity. But how exactly is it going to go to negative infinity? So we want to do some long division here. So we want to take negative x squared and, sorry, just x squared, and we want to divide it by x plus 1. So remember your rules of long division. You're going to get an x up here, then it's going to be x squared plus x here, and you're going to subtract this from this, and you're going to get negative x. And now if I multiply this by negative 1, I'm going to get negative x minus 1. And then I subtract this from this, get positive 1. And so that means I have a remainder of 1. And so what that means is that this piece here becomes, I can write it as x minus 1 plus 1 over x plus 1. That's what the remainder being 1 means, is that this thing actually equals that. How can I verify that? I can go backwards. You can bring them back together, and that's going to be perfectly fine. Now, if I distribute this out, I'm going to get natural log x over x plus 1. I'm going to have this negative 1 over x plus 1. And then I also have negative x plus 1. Now, what do you think about this expression here? This piece is going to go to 0. This piece is going to go to 0. And now the only thing that's really going off to negative infinity is this piece here. So if I came over here and I said, oh, I want to subtract a line from these things so that when I take the limit as x goes to infinity, I get 0. What I notice is that line is exactly this thing here. So what I'm going to want to subtract is I want to subtract negative x plus 1. And that will counter this and make this equal to 0. So my slant asymptote should be negative x plus 1. And let's look at the graph of this. I promise this is going to work out. So if you want to, let's look at natural log x minus x squared, all of that divided by x plus 1. Well, if we look at that graph, yeah, it looks like that is definitely a line with a negative slope, so we're right there. But now, if we plug in negative x plus 1, notice what happens is you can see those two lines actually look pretty similar.